Good morning. We're continuing our lectures on basics of mechatronics. Today's topic is modeling of an electrical motor in MATLAB simulating software. I would like to remind you about the deadlines to upload your LabVIEW report, so please be in time with this. We will start. We will talk today about the different models that are possible to use in MATLAB software. Generally, about the MATLAB, if you are not familiar with this, this is the MATLAB is short name from matrix laboratory. So this is all about mathematical computation that is used for many types of modeling and simulation. And there are many different additional tools in MATLAB. There are ways, if you know the background, if you know the mathematical models and description you want to, or the system you want to create there, you can use the pure MATLAB code, but there are also a set of variable tools that can help you to design complex system in a simple and fast way. Today we'll look those models and we'll discuss the advantages and disadvantages of those models. The good news for Caltech students that we have access for every student, so you can find the link in Moodle in the MATLAB module. You can click there to download. There is a guide how to install and how to get your MATLAB to your own computer. So please do it if you want to do the exercises from your private computer, or also if you want to participate, or if you want to participate in some MATLAB activities, it's better to install on your computer, or if you want to make your project or thesis work with MATLAB, also possible. Important is that you need to have the Caltech email address, and then you will get the licenses. So that was about the MATLAB. So find the link in the Moodle. Let's talk about the modeling and the models. In our everyday life and in especially in engineering field, we use different models of different systems. There are several approaches how to get to the model. During the lectures, we usually discuss the word model of the system. So we have we discussed in the description with words. I try to explain you, I try to show you how one or another system is working, how one or another approach is changing if we change something. So we can basically say that what we are doing on the lecture, especially when we are studying new equipment or we are studying new laws or physical things, so we are talking about the world models. The example, if we talk about an electrical motor, is a description of what it's doing. So an electrical motor is an electrical machine that converts electrical energy into mechanical energy with use of electromagnetic flows and so on. So this is a description how we use it. Another model, what is sometimes might be more useful. This is a graphical model. So that might be a picture, that might be some drawing. When we are describing the parts of the system, so you will hopefully remember this picture from the topic when we were discussing DC actuators. So here is the graphical model of the DC motor. With this cutover, we can describe all the components we have in the model. We can discuss, we can find, and I can show you the different parts, the excitation winding, the rotor, the brushes, and shaft, bearings, etc. So we can discuss the different parts of the model using this graphical representation. In electrical engineering, we are using electrical schematics a lot. So the schematics are presenting different parts, different components of the same device. So, but in this we need more. We put more attention on their electromagnetic properties and electromagnetic laws that we use to describe this model. Here we have the shunt DC machine. So we have the armature winding shown with a bold line. We have the excitation winding that connected in parallel with shunt winding. We know why it's needed. We know that excitation winding produces magnetic flux, and if there is a current in armature winding, we are getting the movement, so our machine starting to rotate. So usually in our lectures, we are discussing all of those models because we can use those models in the different ways, in the different manners, and usually one is adding to another. So sometimes it's not just enough to have the word model or just the graphical model or just schematic model. The model that one more model that is very useful to describe the processes and to describe the physics that happening inside the system is a mathematical model. This is the way how we can show what is happening with our system if some of the parameters are changing. Definitely, we can do the same description. We can do the same model and get the same result if we will use, for example, word model. So we can describe what will happen with the torque of DC machine if the current will increase, and what is Kp. We know that it is construction gain that depends on the machine, electrical machine. We have here electromotive force, we have here angular velocity. So let's say we can combine all of these models. But today we will discuss more this mathematical model because as I introduced previously, the MATLAB, it is all about the mathematics and all about the equations. So here, the way how to do it, how to make them. In our exercise part, starting from the next week, you will get also the MATLAB task. The way is very similar to the first several approaches that I will show you. So the main idea is to use equation, the physical equations, to create the model and start to using this model. But later I will show you also some additional possibilities, additional features, and how to maybe simplify it and how to use it more easy way. Talking about the electrical machines, we have several types. When we just finished the block of the actuators in mechatronics, where we were discussing this electromechanical actuators. Now you know more about the different types of electrical machines. You know what is a DC machine, you know what is AC machine, you know what is the difference between the machine with brush or commutator machine or brushless machine. There are difference between induction and synchronous machines, and also you know now more about the step motors and also more about the servo drives, etc. Today we will focus on the DC machine exactly as exercise that you need to solve during the next 5 weeks. Just to remind you, this is the circuit, equivalent circuit of the DC machine. This circuit we will use to model our machine. Previously in our lecture, we have discussed the different components of the circuit. We have discussed those equations, and we also saw how to get and where those equations are coming from. But let's see once again what we have here. So we have here the electromotive force of the armature winding. So this is the electromotive force that is produced inside the armature when the machine is rotating with angular velocity omega. So we know that armature electromotive force depends on the angular velocity. It means there is no electromotive force produced by the armature when it's not rotating, and the higher angular velocity will have, the higher EMF we will get. We have here also the construction gain, so the K. C, while we have the external, I would say the shunt field machine, so we have the field winding, and this magnetic flux phi is produced by the winding, and by having this external resistance in the field winding, we can also change the magnetic flux, and we see that with the magnetic flux, it's also the linear dependence, so the higher will be magnetic flux, the higher will be electromotive force of the armature winding generated here. The next equation is torque equation. So how the torque, electromagnetic torque, is produced in the machine. This torque we are getting on the shaft of the machine. This will be required when we are connecting the load to our electrical motor, and we want to use the force from the electric motor. The same construction gain, the same magnetic flux, and armature current that is flowing through the armature winding circuit, and we have here also external resistance that can help us to control this current. It means that we can, by having this resistance here, we can also change the torque. We can limit the torque, let's say, because we cannot increase the current in this case, but what we can do, we can definitely decrease the current. And based on the Kirchhoff's law, we have the voltage and electromotive force equations. So we have the voltage, we have the EMF from the armature, and we have the voltage drop in this contour voltage where the armature winding is. So by having the torque here, we need to keep in mind that there is also might be additional torques. There might be additional forces. First of all, the machine itself, it has inertia, So we need to consider the moment of inertia of my machine itself. So it comes from the construction. It comes from the type of the machine, how it looks like. Additionally to inertia, we have the different losses that we have happening in the machine. Winding is made from copper. Copper have its own resistivity, so we need to take into account the resistance of the armature winding. We take into account the resistance of the wires that are connecting there, and everything. This loads the machine. And when we are talking about a real electrical machine, we need to have in mind that there are, even in no load mode, if we have no additional load, we will get the some forces, some currents in that machine. When we are applying load, we need to keep in mind that the load is usually located in the same shaft. I mean, usually it's interconnected to the shaft of the electrical machine. That means that inertia of the whole system is changing. So we need to take into account when we are trying to calculate all the transient processes and when we are calculating dynamics of our system. What we are doing, we can recalculate all the inertia, moments of the inertia to the shaft of the machine to see how it will be looked from the transient point of view. So this equation is also familiar to us because we were discussed it previously. So this is one of the main equations used in one of the main equations used to describe the properties and the operation of the DC machine. So we have here the angular velocity of the shaft. It is here, and it's equal to, everything is coming from those three equations. So from this part, we can find that EMF, armature electromagnetic force over the construction gain and magnet flux will give us the angular velocity. From the third equation, we can get that the electromotive force armature is equal to voltage minus voltage, supply voltage minus the voltage drop on the resistance. We need to keep in mind that sigma R means that we are taking into account all resistances in this circle. So we are at that moment in this equation, the sigma R equals to R external plus RR. But R external can be changed. So we need to have it in mind. And now, additionally, if we will now split it to the two parts, so if we want to have this separately, we can split it in that way that voltage over K multiply P minus armature current multiply sigma R over chi construction gain multiply flux. We will have two separate parts, but from the second equation, we know that the electromagnetic torque is equal construction gain multiply flux multiply armature current. So from this equation, we can get that this speed, angular velocity dependence from the torque will be like this. And due to that, we have here linear dependence between them, we will have the chi multiply phi in square. This equation we have here already derivatives, and they describe actually the transient processes that we will get in case if we want to change the speed. So this d omega over dt shows us how the speed is changing. So basically, we are discussing here about the acceleration. But let's first see the steady state model and see the application of this equation. So once again, I will repeat the equation. Angular velocity. This is the angular velocity that we have on the shaft. We have here voltage, the terminal voltage that we are connecting to machine. We have the construction gain. We have the magnet flux. The magnet flux can be recalculated from the field winding or excitation winding. We have the torque that is created on the shaft, and we have here the sigma that is sum of these two resistances. So having this equation, we can take some part maybe simplify. First, if you would like to describe how the system is working without maybe mechanical part, we can take this middle equation from the dependence from the current, and by introducing by adding to our model the variables, we can calculate the angular velocity. So this is example of the schematics made in the made in MATLAB Simulink. The Simulink is a tool that helps us to visualize the equations. So it used to show the connections between those equations, etc. So it's one of the easiest way how to solve some equations, especially if you have variables. In this example, we don't have any variables, so we have only the constants. So the voltage, armature voltage is a constant. This voltage, the armature current, this one is here. This is the resistance of the armature. If we don't have the external resistance, like here, we use on the armature resistance, so we are multiplying them together here. So basically, this part will be here on the output. There is actually a small mistake in this example, but not that important. Depends on what kind of the variables we will give here. But you see here, this is a plus mark, but it actually should be minus. It's good to have here additional explanation. So we have the block where we will sum those two parts. Construction gain and the flux are multiplied here, and you see that we are dividing here sum, geometrical sum of this upper part to the bottom part, and we are getting the omega. So by having this model in the MATLAB Simulink, we will get the result. So we can calculate the angular velocity for different values of the voltage, current, armature resistance. Construction gain is usually constant, so we're not changing it, and the magnet flux. So basically, what we are having here, we will get one operational point for the system when it's working with those values. This is so-called static model. So in such calculation, we will get only one operation point that with one exact voltage, with one value of resistance, current, etc. What kind of the speed we will get. While we know that if the current depends on the torque, so the higher torque we will have from the loading part of the machine, the higher current we will get here, and it gives us an opportunity to find the characteristic how it will be operate on the different torques. But this will not work if we are talking about the transient processes. So if we want to change the speed from one to another, or we want to slowly increase the torque, that will not work. What to do, or how to introduce the dynamical model. For the dynamical representation of the electrical machines, we usually have more complex equations. The same equation that have been discussed previously will be more complex because, generally speaking, if we are changing one of the parameters, for example, angular velocity, or in transit, okay, let's say we are changing the torque, we are increasing the load here. So by changing the torque, we will get the higher torque here. It means that the IA, the armature current, will change. If the armature current will change, also it will affect on the this part. So due to the fact that voltage will be constant, this depends on the angular velocity. We will have the different operation point in different systems. So a lot of parameters will change at the same time. More complex will be when we will start to change the angular velocity. If we would like to, for example, start our machine, because when we are starting electrical motor, the starting speed is 0, and by starting the machine, by implementing the voltage, we are getting higher electromotive force. With a higher electromotive force, we are getting also here the big difference. There will be unbalance, so we'll change many different parameters. And all this changes that are happening in the transient mode may be definitely described in the different models. One example of this model that we are quite often use for the transient processes are the DQ model, or so-called direct and quadirect model. So this is a model of an electrical machine that takes into account the different directions of the system. So this is easy to describe if the construction of machine is different. What I have in mind about the different construction, that when we were discussing these DC machines, for example, here you see that we have the armature or the rotor that have such rectangular form, and by direct and quadirect axis we have very different parameters, very different fields. The magnetic field that will produce this winding, the field, the armature winding, this will be directed in one direction, but while we have the electromagnetic processes that are not only directed in one direction, there will be some magnetic field that will be looks like this and like this. So we need to consider what will be on the quadratic axis, and this is what we need to keep in mind when we are talking about the transient processes, because both of those magnetic fields will change due to changing of the parameters, and having this in mind, we need to describe this is in the similar way. One of the representation why I want to show you this on that slide, because there is a combination of different possibilities, so of different things what can be changed during the different transient operations. And with one transient model, we need to describe all those possible changes. And usually in mathematics, we are describing these changes in the matrix. And here is the different options, different possibilities how to change it. By changing this, by having this as a matrix in the matrix form, we started the lecture with this with the topic that MATLAB is everything about the matrices. So basically, this how this MATLAB can help us to solve this problem. All the equations in the transient will be more complex because there will be several options, several possibilities of these equations, many different combinations, and these combinations are described in the matrix. So there is a way how to do it in the MATLAB. When we have the complex equation and complex system, one of the, especially when it's changing, so we have here derivatives, so we have the process that is changing. Also, coming back to higher mathematics that you have studied at the university, one of the way how to solve such equations is using different transformations. One of the transformation that is widely used in the engineering is Laplace transform. So we are by having this derivatives here, we would like to describe and would like to linearize the system and would like to make the system more simple for us. So we are describing the same equations with transfer functions. Here is the different transfer functions for different states. So what if we will change the one or another parameters and how one and another parameter depends on each other. As I previously mentioned, they are interconnected, all of them. And here is the way how those transfer functions can be described. In MATLAB, we have the possibility to use those transfer functions. So all those transient processes, if we know how to describe, if we know those mathematical background, we can represent as a function or so-called transfer function. If we know exactly the parameters of the electrical machine, so you can see in our transfer function here, we still have the values that are very similar to the, or not similar, but exactly the values that we are getting from our electrical machine. Sorry, so we have here the armature resistance, armature inductance. Inductance here is very important. So in the static model, we didn't discuss the inductance because in the static model, in the static operation, the DC motor, we have the constant current. At the constant current, the inductance of the coil, inductance of the winding is not changing. In case of the transient, if we're starting to change the value of the DC current, we are getting the different values, and this dependence is not linear. That's additional thing, and this is additionally needed to be introduced also in this equation here. You see, so it's not only the active but also inductive load taking it. So that's we need to take into account. And such complex model is already describing us the system in the dynamics. So we can see what will happen if we will change the speed, if we will start to accelerate or decelerate with our electrical motor. Definitely, this model number 2, what is a dynamic model, is much more functional, because in case if we will have the variable with a fixed value, so we are increasing, for example, speed from 0 to the rated speed, and then the machine is operated for some time at the rated speed, we can see that it will go to the steady state mode, and it will show us exactly the same value as the static model shows. So the transient or dynamic model will show us exactly the same values as the static or steady state model. But in opposite, it's complex to do. So this model is more advanced. Definitely to building such models and to using the Laplace transformations, we need to know more about the physics that happens inside the system. We need to know more about the electrical machine we use. We need to have the proper description. We need to understand all the equations, where they come from. As I mentioned previously, in the MATLAB, there are some models, some blocks that are made to simplify the work of the engineers, because this is not the first time in the history when we are talking about the models and about the computer modeling, right? So there are a lot of the engineers who need to solve this modeling problem basically every day, and they need to get those calculations. They need to calculate the value of the speed, current, magnetic flux for different types of the model. In introduction of the models, I said that electrical engineering, we use a lot of the schematics, and those schematics help us to describe and help us to show some typical processes that are happening inside the system. So we know that inside of the armature winding, we have the active resistance, we have inductance. We have the same thing in the field winding. We know that we need to feed one and another with a current. So this is the armature current, this is the field current, this is the values, how we can get them. And if we have the model, if we know that our winding might be represented by active and inductive, active resistance and inductance, we can have, and we know what is the reaction of these two components, we can simplify and can use the block. So the MATLAB Simulink in special libraries, it has the models that can imitate those connections. What is important for us that as engineers, if we would like to use those models, we need to know how those models should be connected, how these components should be connected to each other. So in other words, we need to know this part of the model, right? And additionally, we need to know how they are interconnected to each other. Those are different parts. So this is a part of the bigger model. But in here, we still need to understand what is happening inside. Why I'm talking about the bigger model? Because here you see the inputs and outputs of the armature and the field winding. So this is just a part, because we need to understand how it's connected inside, but then we need to see the reaction from the outside. So what we have here? We have here actually three parts. We have here the field current, so we have here the excitation winding. We have here armature circuit, armature part that is rotating. So basically, this is the stationary part. This is the electrical part of the rotating component. And you see, we have here the mechanics block, and this is the separate part. So this is the part of this model that describe the operation, what is happening on the shaft of the electrical machine. And usually we cannot represent them on the, we can see the reaction of mechanical part to the electrical part, but we cannot describe, we cannot represent them on the same equation or on the same part. So we know reaction from one to another. And that's why sometimes we need to focus on those parts that in that way that we need to organize our models or separate the electrical and mechanical part. And because in the mechanical part, we have our own laws, our own dependencies, and there is looks very different from the electrical point of view. I mean, what we can do, we can calculate the electromagnetic torque from armature current. We can we know we need to have the magnet flux calculate the electromagnetic torque. So the magnet flux is coming from the field current that is here, and here you see the transfer function that takes into account all the dynamics that's happening inside, and the system is not linear, so we need to have this in mind. And based on this, we need to have the idea of what is the loading torque, because they need to be balanced. And then the inertia comes through, and then the integration, etc. So this is so when we calculating, when we're taking into account these two torques, the torque that coming from the load, the torque that is produced by electrical machine, we are generally speaking calculating, we can get the angular velocity, but we know that if the angular velocity is changing, it will affect us and the system. There is a moment of inertia, and the angular velocity is also affecting on the field current and the electromagnetic force. So we basically closing the loop, and all these processes that we're having in our DC machine, they are interconnected. In our model, what we have done on this example, we have the separate module to measure all these values. So you see, we can have here an output, external output, to measure the angular velocity, armature current, field current, and electromagnetic torque produced by the machine itself. This is important if you would like to describe the performance, we would like to describe this, how the system is done. So this model is a part of the electromechanical library in the Simscape. So if you will install the MATLAB, if you will open the Simulink tool, you can go to the Simscape library, and in the Simscape library you will see such model. So you can see this is a representation of DC model. In the similar way, you can get different types of this model. So this is a DC motor with a separate excitation. We can get the DC shunt motor. They are different from the performance point of view, but as I mentioned previously, while we are not the first who are doing this, we need to know or we can use ready models. There is one thing with those ready models that I will mention later when we'll discuss a little bit different models. Because if you would like to model the electrical motor, you need to understand that all the parts, all the variables inside the electrical motor are interconnected to each other. And the models, the motors are different by size, different by type, and sometimes it's not only enough just to show the different power of the motor, because in the here, if you will use in the Simscape this block, when you double click on it, you will open the window that will describe you what kind of the model you have. So it will describe, give you a hint how to connect it, why this minus plus, what does it mean, what is the permanent magnet here, and etc. But also it will ask you an additional parameters of the motor. So you will be needed to add here the armature resistance. You will need to add here the armature inductance. You need to calculate the back electromotive force here. You need to add here some mechanical parameters here, etc. In MATLAB, what I really recommend you to do. So there is, as I said, there are a set of the prepared models in the MATLAB, and we are not the first engineers or the first scientists who are looking for these models. In MATLAB, in that case, there are several examples and several ready solutions. What can you use for studying and understanding what is happening? For example, if you will type in MATLAB, if you just open the MATLAB, if you have installed those Simulink toolbox, if you will just in MATLAB in the command window write the EE water brushes DC as shown on the slide, you will get you will open this example that will show you how the machine is operating, what are the constants, what are the power sources you need to add here, etc. Question will be about what to do, how to do, and how to use. So there will be some instructions in MATLAB of how to use them. So there is possibilities to plot or print out the speed or speed torque characteristic. What is good in this kind of examples, that you will be able to change the different parameters of the machine. So you will be able to change the different voltages. You will be able to change the ramps, and by changing this, you can see the reaction of the model, and you can understand how the machine, how the real machine will behave and will operate. You can here, for example, switch from the no load to the load mode, etc. You can change the load here because it's given as a constant. You can try to maybe replace this constant block with a variable load and see what's happening with this machine, etc. So my recommendation to you, if you are would like to use, or you would like to create your own model for not the exercise blocks that we have in the course, because for the exercise there is a straightforward manual. If you are following this manual, you just get to the solution and that's it. But if you want to do more, if you would like to use some type of the electrical machine or actuator in your project, in your thesis, I recommend you to start with playing, spend time to see the reaction and see how it operates, because you will get this different values, you will get this different characteristics, and you will see how it's changing, how it's accelerating, how it's accelerating. So you will see all those trends, and you will see when it will become stable, what are the torques required, etc. So this is example. You see that the tested motor here is starting to rotate in one direction. It rotates for 1 second in one direction, then it stops changing the direction. You see how the transient is happening, how long the transient is. In this case, the load is not that big, so the machine needs a little bit torque just to change, and then after the second it's stops, so we can see that how it stops and how the command is operated. So without load, it looks like this. If you will switch on the load with this switch, you will see the totally different examples, and you will see the totally different picture, and you can compare these things. So we have discussed several models of the DC machine. As I said, there is many different possibilities. We can start from very simple steady state models, go to the transient using the different Laplace transformations, and then we can go to the other types of the machines also. But once again, I showed you the more in details the DC machine because it's kind of simple. There is linear dependencies between the many parameters. When it comes complex, more complex when it goes to the transient. But if we're talking about the AC electrical machines, in AC electrical machines, we have non-linear parameters, and this might be more complex. And all the equations are also complex. So for the one example with a synchronous machine, we also use here the two-axis model, so the direct and quadratic, and the reason is exactly the same. So this is one of the possible representation of the synchronous machine, or one of the possible type of the synchronous machine. The reason is exactly the same. So you see that the magnetic fields and all these equations will be different in two axes. Usually the machines are symmetric, so we can there is enough to have two axes. If there will be more poles on the rotor side, we can maybe play with the machine. We can shift the axes, and in our calculation we need to keep it in mind. But what I'm trying to say that the equations that we will get, there will be more complex, and there will be the direct axis equivalent circuit, and this will be the quadratic axis equivalent circuit. The direct axis equivalent circuit is a little bit bigger because we have here higher resistance. We have the additional magnetic flux that is produced here, so we need to keep it in mind. And you see that the equations that are coming here, there will be more complex and more derivatives we will have here. In this example, we have the inductance that is shown as black rectangles, this is according to the German standards. So if you will read the books related to electromechanical actuators, electrical machines in German language, for sure you will find some descriptions like this. So I showed you previously there was also another symbol for the resistance, because we have the EU standards and US standards, and also inside the European Union we have also several different standards. So we need to know always keep an eye on it and to understand what is exactly the symbol means. So this is once again the idea of those engineering things. So you see that these equations are more complex, and definitely if we will do the Laplace transformation of such QD model of the synchronous machine, we need to do it separately for Q axis, for D axis, and we need to have maybe several transformations. But as I mentioned previously, also in MATLAB there is already the built-in models. There are the models that are created for us, and they are created with some examples. So in the same SimScape model, you can find the synchronous machine. You can find the same description. So you can find what is how the machine is work, how it's operate. But you see, when we are talking about the DC machine, there was just a few parameters that we need to enter to start this machine, to start to work with this machine. In synchronous machine, we have more variables. We have here the different leakage inductances for the direct and quadratic axis. We have here the stutter zero sequence inductance that is also needed for the magnetization. We have here the parameters of the field and twining, etc. Additionally to those things, we will have the mechanical parameters, the same as it was in the DC machine, because the mechanics, in this case, from the point of view of reaction of the load, it looks very similar. But then we will get an additional module that will allow us to add some starting variables. So if our starting current or starting magnetic flux is not zero, because in case of the synchronous machine, it might be so that we have some leftovers from the previous exploitation of the machine. So when we have some magnetic flux left from the previous run of the machine, we can introduce it, or we are starting from some situation that the machine was under the load, then it's something happens. So that's additionally we can describe everything here. So all those parameters we need to have in mind, and definitely we need to know what exactly we are trying to model. In a similar way, there is an example of the synchronous machine. So one of this is state synchronous machine state space control. There is not only the about the electrical machine, but it's also about the control techniques and different application of this technique. So once again, you can run these different examples, see how to create the results, how it looks like, You can maybe run this with a different excitation currents, try to change maybe parameters of the machine, and then you will see what will happen. But this definitely requires additional skills and additional understanding of what and how. So if in the theory class from another subject where you maybe discuss more closely the topics related to electrical machines and operation of electrical machines, the professor will say to you that how the current or how the loading torque affect the current. You can just basically here increase the load and see what's happening with the current. You can maybe overload the machine, etc. So you basically can test the machine without the real testing, and that's how we use those models. Well, I tried to show you like several examples, starting from the DC machine, what is linear, but in the transit mode goes more complex. Then we have the synchronous machine that actually use both of the currents. It has AC and the winding on the stator winding. It has DC on the excitation or field winding, but we have more complex machine. What is induction machine? From the operation point of view, it's simple one. We know how it operates. So we have discussed it, and I also mentioned that it's used a lot in everyday lives and in engineering. But at the same time, the operation principles are more complex. The equations that are describing the connections between different parts of the system is also more complex. So induction machine is more complex type of the machine for modeling. And here we definitely need to use, we can also use the same approach of the machine, but we need to keep in mind that here with a DQ models, even with DQ models, we have very different approaches. And even with a static model, the machine will be quite complex because the stator part is magnetically connected to the rotor part. And there is a magnetical part description is here. And even if you would like to introduce such kind of equivalent circuit, it will be complex. But when it's going to the transient processing and going to dynamics, we need to keep in mind that each of the winding of the machine is affect on another winding. So it's basically starting to produce the electromotive force, and that it will be directed to the different direction, or it can be changed based on the operation mode. So we need to keep in mind, and you see that those equivalent circuits of the induction machine becomes quite complex and non-linear. This is the most important part, that it is totally not linear. Additionally, there is like the same situation. So if you will take from the SimScape the induction machine block, then you will see the parameters, different parameters here. You can change here the power, voltage, but what I really want to say, please be careful with this, because there is a set of examples in the MATLAB that are prepared by the engineers or by the MATLAB engineers, and they know what is inside the machines that they are trying to use, they are trying to show for you. Because with a different power, we will have a different parameters inside the machine. So the starter resistance, the starter leakage inductance, and so on, all those things are affecting on this power. And this is basically, if we are changing here, it will be changed here. But it's not it's not the question of the calculation. It's a question of a number of calculations. So we need to recalculate. We need to estimate, and it's not working in the opposite side. So it will not work. So if you will just change the power here, and you will accept it, please don't wait that the values will be changed here also. Here is the same equation with the saturation at the magnetic properties. So those non-linear models are more complex. But once again, there is an example of the induction machine, how it works. So in the similar way, you can see what are the operations, how the currents are divided between the different parts. You see here is even the voltage in the boost bar. So basically, in the real life, when we are operating the induction machine, it's not possible to measure the voltage of the bus bar because the short circuit rotor has no possible connections to this. But here, theoretically, we can do this and we can get this. The same thing might be with the we are definitely have another model. So the stepper motors are also here, and here is you see also the different parameters of the stepper motor. So once again, you need to know those parameters. I really want to once again say this, that please just not change the power of the machine and try to simulate, because with the power of the machine, many different parameters are changing. The exercise that we have prepared for you for DC machine will exactly show you that different types of the machine will have very different parameters, and you need always to keep an eye on it, and you need to recalculate it. Yeah, so this is an example with a stepper motor, also a very popular motor in the mechatronics nowadays. So it's good to understand how it works. It's good to see the how it can be controlled. You remember last week we have discussed this different control modes. So there are possibilities to switch the pulses, to change the shift between pulses, and to see what is the angle and how the steps are going. So there is so many different applications. So for example, if you would like to create maybe some control waveform control for your device, and you would like first to see how many revolutions or how many steps it will do, you can definitely use some examples from the MATLAB to see how it can be operated. What is also good in MATLAB, that they have not only the motors model, but as we discussed in the actuators module or actuators lecture set, that it is important to have the motor together with the control system, and this system may include also some mechanical part. So all this complex system with power electronic model, with electrical machine, with mechanical transmission, it's called drive. So there is a set of the full drives. So we don't need to model them separately, because modeling of the power electronics is challenging itself. It can be also complicated. Modeling of the mechanical part is also kind of complicated. So we can get the different models from the already available library. And at the same time, the same way, this will be interesting to check them and to see how they work and what is inside there. Yeah, so that's